For our project, we wanted to explore the applications of calculus within disease epidemics. An epidemic is a large short-term outbreak of a disease. Human epidemics are often spread by contact with infectious people, and there are many kinds of contagious diseases that are easily spread through casual contact. By identifying the main effect, we can formulate a model that is simple enough to use to compute and predict the overall spread of a disease. We plan to develop a model that predicts the growth of an epidemic, in this case, the coronavirus. Our main goal is to chart the long-term change of the virus. In order to create our model, we will have to make a few assumptions. First, we'll have to assume that all individuals fit into one of these three categories that we later use as the variables S, C, and I. Those who can catch the disease, those that can spread the disease, and those who are immune and cannot spread the disease. Secondly, we also have to assume that the population is large, which is a reasonable assumption. Thirdly, we also have to assume that after contracting the virus and recovering, people are immune to the virus. Finally, we will also have to assume that our population is well mixed with people interacting with the same fraction of people in each category. For our model, the variables that we will be using are T for time since days since observation, which is at T equals 0, S for individuals susceptible to the virus, C for individuals who have the virus, and I for those who have contracted and recovered from the virus. Time T is the independent variable, and variables S, C, and I are dependent on time. We will have to add two parameters, A and B, to mathematically describe how individuals move amongst the categories. These parameters will have fixed values that...
So first, we will have to figure out how someone recovers from the virus. On average, it takes about 3 weeks to recover from the coronavirus. Therefore, the contracted category consists of individuals who have the virus for 1, 2, 3, or 21 days. On day 22, an individual moves from the contracted category to the immune category. We can assume that the different groups in days in the contracted group are roughly of the same number. This permits us to say that the number of people moving from the contracted group to the immune group tomorrow is equivalent to 1 over 21 of the contracted category. In mathematical terms, new people in I, which is the immune group, is equivalent to 1 over 21 times C. And the units in this is peoples per day. The next thing we must figure out is how one spreads the virus. If a person with the coronavirus is sitting in a room full of individuals who are susceptible to the virus, then they will all most likely contract it. However, if a person with the coronavirus is next to someone who is immune to the virus, they will not contract it. We can assume that we can find an average number of contacts per person with the virus has made, which can be denoted by the parameter R. So in our case, R will be the average number of people at risk. Now we need a parameter that confines contagiousness, which is A. So A will be the contagiousness of the virus. The number of people at risk per infected each day can be given by A equals R times B. And in this case, B is basically the new people in the immune group. This means that if C people have the virus on a particular day, A times C equals the total number of people at risk every day. The contact of people with the virus and those susceptible to the virus creates a new cases of the virus, which means we must multiply this total times the fraction of people susceptible. The parameter N is the fixed total population. Therefore, the number of new cases of the coronavirus are new cases tomorrow is equivalent to A times S over N times C, where N is the fixed total population. Now we can start making equations to model change in our categories. So an increase in S tomorrow can be given by negative A times S over N times C. An increase in C tomorrow can be given by A times S over N times C minus B times C. And an increase in I tomorrow can be given by B times C. The change in a function of time as f of t as time changes from t to t plus delta t is given by f of t plus delta t minus f of t. Therefore, we can say that f of t delta t minus f of t all over delta t is equivalent to negative a times f of t over n times c delta t. And we can also say that ct plus delta t minus c of t over delta t is equivalent to a times f of t over n times c of t minus b times c of t. Oops. There. This allows both sides to be written as rates of change. We write this form as a rate of change in units of numbers of people per day. So we can say that f of t plus t delta t minus f of t all over delta t is in numbers of people per day. So this is just our units. Dividing both sides of the prior equation by n results in f of t plus delta t over n minus f of t over n times 1 over delta t is equivalent to negative a times f of t over n times c of t over n. In terms of fraction variables, the rate equations become delta s over delta t is equivalent to s of t plus delta t minus s of t all over delta t. And this is equivalent to negative a times s of t times c of t. And we can also say that delta c over delta t is equivalent to c of t plus delta t minus c of t all over delta t, which is equivalent to a times s of t times c of t minus b times c of t. Now we can calculate the derivative, and we can say that d of s over dt, which is equivalent to the limit as delta t approaches 0 of delta s over delta t, which is equivalent to the limit as delta t approaches 0 of s of t plus delta t minus s of t over delta t. And we can also say that dc over dt is equivalent to the limit as delta t approaches 0 of delta c over delta t, which is equivalent to the limit as delta t approaches 0 of c of t plus delta t minus c of t over delta t. for which we have already written the equations above. The key question in our model is that we want to answer the long-term change of the coronavirus. If some people never get sick as T increases, S of T will never reach 0, but will stay above the fraction of people who are immune to the virus. Because S of T can only decrease, we are trying to find when either the limit as delta T approaches infinity of S of T equals 0, or the limit as delta T approaches infinity of S of T is greater than 0. So in order to do this, we can now that we have a model, we can use a computer to solve this equation to understand the long-term change of the coronavirus.
Using New York as an example, we can estimate the total population variable n as 19.45 million to be the horizontal asymptote, as there cannot be more cases than people living in the state. During the month of March, new cases averaged around 6,000 people daily. We can let that equal C, as it gives an idea of the infection rate per day. However, there are obviously more people who are susceptible to the virus, such as people who live in bigger cities. Therefore, we can assume that New York City's population, which is 8.4 million, would equal S. On average, an infected human spreads the virus to 6 other people, therefore making that our A value. Parameter B, on the other hand, is variable based on how many days the person has been infected, but once it reaches 21, the person is deemed immune. Using these equations, we can plug the values of infected patients to predict the estimated number of people infected at any given time if shelter in place was not instilled.